Hello, Calc students. How are you today? Today we're going to be talking about related rates. This is going to be our first opportunity to get involved in calculus in the, if I want to say calculus in the real world. We've been hitting a lot of individual skills, product rule, quotient rule, chain rule, power rule. All of these different aspects are coming to play here. But now we're going to talk about what's going on in real life. So to begin with, I would like to take a look at the situation right here. What you guys are seeing is a particle moving. Hopefully you're seeing a particle moving along this graph. I wasn't expecting quite the lag that you guys are experiencing right now, so I apologize. There we go. I think it's a little bit better. So we want to analyze how is this particle changing as it goes along the parabola. One of the things that you will notice is that um, the speed of this particle is going to change. So right now it's going fast, it slows down, and then it speeds up and goes faster. I'm looking more in the positive direction as opposed to the negative direction. So analyzing the speed a little bit more closely, one of the things that we're going to notice is this change, this horizontal change that it was going through was being done in a constant manner. It was the vertical change that was changing how fast it was going. So I'm going to move away from this because the lag is pretty bad. But anyway, so the horizontal change was constant, but the vertical change was actually not. Um, Vertical change, as we saw that it our graph, we decreased on the graph and then we increased on the graph. What this means is that the two are working independently of each other, and we can analyze what's happening to all those different components at the individual moments. So that situation modeled this problem right here, which is why I'm going to start with example number 2. We had this curve that was on the graph of y equals 4x squared minus 2x plus 1. And what we did was we established that we had a constant horizontal velocity of 3 units per second. So with this constant horizontal velocity, what that means is the rate of change of x with respect to time was 3. Our goal then is to find the vertical velocity. Our vertical velocity is going to be our dy dt. Well, how am I going to figure out what dy dt is? And then this is a perfect example of why implicit differentiation is needed, because what we're going to do is we are going to take this overall equation right here. We are going to differentiate it not with respect to x, but with respect to time. When we do that, we now have this equation where we're trying to solve for dy dt, which means we get 8x dx dt minus 2 dx dt. Officially, it's going to be plus 0. But this means that we can fill in all the information that we have to find the unknown value that we don't have. So we know that x, let me change colors here quickly. We know that dx dt is 3, so we could plug 3 in right here. We know our x value is 1, so we could plug in 1 here and solve, and we get dy dt ends up being 18. One of the things that I'm going to ask you to do is I'm going to ask you to write all of these answers in a complete sentence for us. The reason why we're doing this is we want to establish the meaning, the context of everything that's going on. And I have this acronym that the AP taught me. It's NUT. NUT stands for noun, unit, time. Noun is going to be the context of the problem. U stands for unit, and T stands for time. So every problem, when you analyze it or when you come up with like a real life example, you're going to want to have noun, unit, time. Our noun in this case is the vertical velocity because that's what we're asked to find. The unit is units per second. Now the number or the value that comes out of the mathematics typically goes in there as well. One of the things that I will never do is suppose you made a dumb mistake and you said, hey, that was 23. You put 23 here, I'm not going to count you off in your final answer as far as looking for noun, unit, time, just because at this point I want to make sure you understand what exactly you are trying to do here. And then our time frame. If you notice, time isn't really like a value here as much as when x equals 1, that's the time frame of what we're referring to. So noun, unit, time. Please make sure you have that in all of your answers. The first problem, we have a 13-foot ladder leaning against a house. Base of the ladder is sliding away, which, as you can see, I'm highlighting here, it's sliding away. So I labeled this situation where I have my 13-foot ladder leaning against the wall. This base distance is changing, so I'm going to give it a variable name. This height along the wall is also changing, so I'm going to give that a variable name. What this means is, I mean, we can call any variable that we want. I'm using y vertical distance. So dxdt is 3. And because we're moving away from the wall, x is getting bigger. Because x is getting bigger, this is a positive 3. If that x value is getting smaller, then we would have a negative 3. Now, as that x gets bigger, what should happen is the y value gets smaller. And so dy dt, when we find it, which is what we're supposed to do, we want to find how fast the top of the ladder is moving down the wall. So dy dt should end up giving us a negative value. So big question is, what models this situation here? X squared plus y squared equals 13 squared. So this is a great Pythagorean theorem problem. So we differentiate that with respect to time, and then we plug in the information that we know. So we know that the base instantaneously is going to be 12. We know that 3 feet per second is going to be our dx dt. Now what we don't know is we don't know our y value. And this is where we're going to refer back to what is the overall situation. We could use the instantaneous moment to figure out our y value. And once we know our y value, we can then solve for dy dt. So big thing to look for. We have a general model that we're going to be working with. We're going to have an instantaneous model that we are working with. So when we say the general model, it should be true for every part of the situation. The instantaneous is what's happening at the time frame that we're looking for. And then make sure we answer the question appropriately. The ladder is falling at a rate of 7.2 feet per second. Or we could say the height of the ladder is changing at a negative rate. Both would be appropriate. And just as a quick noun unit time, ladder is falling, there's my noun. Units are feet per second. And then time frame, when the base of the ladder is 12 feet from the wall. Noun unit time. Example number 3, water pours into a fish tank in the shape of a rectangular prism. How fast is the water level rising if the dimensions are 2 feet by 3 feet? So we know that rectangular prisms, the volume is going to be the area of the base times the height. Well, this is a constant area of the base, which is how I said, okay, area of the base is just going to be 6 times the height. So we have water pouring into the fish tank. I strongly encourage you to draw a picture just to help you get into that situation. And water is pouring in at a constant rate. And that water is filling up the tank. So how fast is the water level rising if the base dimensions are 2 feet by 3 feet? So those 2 feet by 3 feet are how we got the area of the base to 6. So dv dt is always going to be 6 times dh. Now, if the, this is where something I skipped over. This 3 cubic feet per minute, the fact that this is cubic feet per minute tells me that this is going to be my change in volume with respect to time. That's why dv dt is 3 over here, and then dh dt is always going to be a half, meaning the water level is rising at a rate of 1/2 feet per minute. And the way that I get this unit, there's my u, by the way, is I take a look at whatever units are involved here. Dimensional analysis from chemistry might be very useful here. So second problem, how fast is the water level rising if the base dimensions are 30 inches by 48 inches? One of the big things that I encourage you to please keep an eye out for, your area of base is not 30 by 48 because now this is 30 inches by 48 inches, which means we have to convert our inches to feet. So 30 inches is how I get my 2.5 feet. 48 inches is how I get my 4 feet. And then I go ahead and solve dht is 0.3. So the water level is rising at 0.3 feet per minute. Example number 4, water pours into a conical tank. Let's go ahead. Water pours into a conical tank with the point down of height 10 feet and radius 4 feet. Now that water is pouring in at a rate of 10 cubic feet per minute. Once again, there's my dv dt. So anytime I get some information, dv dt. How fast is the water level rising when it is 5 feet high? And this is So when the water is 5 feet high. So this is where we have to draw our overall cone. So we have a cone here. We need to know what is the volume of a cone. The volume of a cone is 1/3 pi r squared h. Suppose you didn't know that, what could you do? You could always just ask Siri to see what that volume might be. So let's fill in what we know. Do we know the radius? And this is a little messy right here. So let me try to clean that up for you, right? I guess that like took out the entire answer. So anyway, do we know the radius? Do we know the radius of the water? And the answer is no, we really do not know the radius of the water. Do we know the height of the water? Well, instantaneously, we know that the height's going to be 5. How is that going to help us? Well, that water level is changing, so I really should call this an h to begin with. So now, what I could do is I could look at it and say, all right, hold on just 1 second while I pause. So sorry about that, guys. I just had somebody walk into my classroom and I didn't want it to affect the video. So anyway, moving on. Where I was I was trying to figure out how fast the water level is rising when water is 5 feet high. So I'm going to start off with my overall volume equation. One of the things I'm going to notice with that volume equation is I have both the radius and the height. And at the unknown, there's no way that I'm going to be able to figure out my radius unless I have some additional information. That additional information is going to come from the hidden similar triangles that you should see right here. So I drew that down here, and those similar triangles are something that you're going to have to keep an eye out for because they show up in random places. AP loves to make sure that they assess that. So our similar triangles, we have a height to radius ratio of 10 to 4. So what that does is that gives us this overall relationship of 5r equals 2h. The question is, what do we want this in terms of? Since I want how fast the water level is rising, I want to know what the HGT is. So I put R in terms of H. Now, since R is in terms of H, I can go ahead and substitute that into my volume equation so that I have my volume is 1/3 pi times 4h cubed over 25. So now I can just answer my question, how fast is the water level rising when it is 5 feet high? Well, when that height is 5, plug it in and we get 10 over 4 pi cubic feet per minute. So because we want to know what dVdt is, and I know I kind of through all of that. Anyway, time passes, what happens to the rate at which the water level rises? The water level should be rising at a decreasing rate because since our radius is increasing, then that means that our volume is going to be decreasing. Now, there are lots of different ways you can kind of think through that. As the height's getting smaller, or as our height's getting bigger, the radius is getting bigger, which causes the volume to end up being smaller. So, all right, example 5, sand at a gravel pit. Sand is falling off a conveyor belt onto the conical pile at a rate of 10 cubic feet per minute. So this is a situation that I have not drawn out yet. So we have a conveyor belt, and then sand is dropping off of that onto a conical pile. So let me go ahead and draw that out, but really this is a conical pile. So we have the height of the cone and then the radius of the cone as well. So at what rate is the height of the pile changing when the pile is 15 feet high? So we want to know that the overall pile is 15 feet high. So this is an instantaneous moment, by the way, which means as I look at this from the beginning, I have to say, what is my overall general situation? Volume is 1/3 pi r squared h again. So now I want to know what height or at what rate is the height of the pile changing. So once again, I want to use my similar triangles. I think I didn't show the similar triangles here. But excuse me. So I want to know what my radius is, right? So I can set up my similar triangle to say that 2r equals 3h. Now, how did I get that? The diameter of the base is approximately 3 times the altitude. That's where I translated that into the diameter of the base is 3 times the altitude. So r equals 3 halves h. And then I did say similar triangles, but there weren't really similar triangles here. That was the additional information to help us. I'm just so on this similar triangles kick. I apologize, guys. So anyway, my radius in terms of height I could plug it in there and pretty much simplify my overall expression. One of the things that I could do, and I don't have this written in the notes here, let me go ahead and clear this area off for you guys. What I could have done here is right from the beginning, I could have said, okay, dv/dt, I could have treated this as a product rule. Let's call that, that part u and then h is v. So v times 2/3 pi r times dr dt. So v du plus u dv. So v du plus u dv. Now, in this case, I now have more variables than what I started with, and it is more complicated. But what I could do is I could differentiate this and say dr dt equals 3/2 dh dt to develop some relationships that if I really, really wanted to, I could then take this and plug all of that information in, as well as knowing what my height is. So I know my height. I can figure out my radius through this equation. I know dr dt and I know dh dt based off of all this information. So long story short, I could have done all of that if I really wanted to. However, this is a much more simplified approach to the problem. Example number 6, the spy tracks a rocket through the telescope to determine, one of the things you'll notice is I did not answer these in complete sentence. My apologies. So should I do that? Let's do this. So when the height of the pile is 15, or when the pile is 15 feet high, 15 feet high, it is changing at a rate of, and it also occurs to me that for some reason on here I don't have that answer. I think I might have erased it. At rate of 9 pi over 4, then our height is 15 squared, and dh dt, where is that piece of information? 10 cubic feet per minute, so times 10. And it's changing, that ends up just being feet per minute. So I apologize for the shortness of that, but anyway, moving on. Spy is tracking the rocket through a telescope to determine its velocity. Rocket's traveling vertically, located at launch pad 10 kilometers away. So 10 kilometers away, the height's changing vertically. dy dt, we know that that's going up. So is there a relationship that I have here? I have an angle theta. This theta, I have the y relationship and I have the adjacent relationship. So that prompts me to think that I'm going to be using tangent of theta equals y over 10. Differentiate it to find the instantaneous change. I do know that in this information, the angle between the ground and the telescope is 30 degrees. So I can plug in 30 degrees for my angle. Secant of 30 is going to be 2 over the square root of 3. And when we square it, we get 4/3. Now, when I go ahead and simplify that expression, dy dt ends up just being 20/3 kilometers per minute. One of the things that you do want to look out for is when you have an angle changing. So this d theta dt, when you have your d theta dt, that is going to always be in radians. Radians isn't its own unit specifically. It kind of like merges all the other units that are there. So just be on the watch for something weird that happens to the angle. Like how's the angle changing? It's always going to be in radians per whatever time unit. And the last problem. Baseball diamond is in the shape of a square and has sides that are 90 feet long. During a play, runner advances from second base to third base. So we're looking at of that nature, second base and third base, at a speed of 15 miles per hour. So one of the things that I do want you to know that these are in feet, and this is miles per hour, which means we have to do a conversion from miles per hour into feet per second. There's your dimensional analysis that occurred there. So what rate is a player's distance from home changing the moment he is 30 feet from third base? So as we're taking a look at this overall situation that I'm about to highlight, as the player is advancing to third base, you should see that the distance to home should be getting smaller and smaller, because what happens is it goes from here to here to here. Anyway, the distance is getting smaller. So with that in mind, the SDT that we should find ends up being negative, and cut to the chase. It is. I was in erase mode instead of circling mode. So let's take a look at this redraw that I did over here. I once again have some Pythagorean theorem that's going to be going on. So x squared plus 9d squared equals s squared. So general situation is right here. We take the derivative to, so let me write that as general. Take the derivative to find the instantaneous situation. And once we have that, then plug in the information we know. One of the things that you see that I did here is I ended up just dividing by 2 because we didn't really need it on both sides. But anyway, so I don't have it written here, but 2 times 30 times dx dt, and that's where the negative 22 is going to come into play. The reason why dx dt is negative is because this distance here to third base is getting smaller, which is why I count x as a negative value. Sorry, dx dt is a negative value. Equals 2 times s. Well, how do I figure out s? This is where I'm going to go back to my general situation to figure out that my s is going to be the square root of 9,000 times ds dt. And we could solve for ds dt by dividing both sides by 2 times the square root of 9,000, which gives us that overall answer. Now, let's go ahead and write this out in noun unit time. So when the player is, bad handwriting, is 30 feet from third base, his distance to home plate is decreasing by 6.957 feet per second. So somehow we have to get that direction of the negative involved there, which is what I did. So one of the things that you're going to find is every single problem is going to be entirely different, but the approach is going to be the same. Our approach is that we'll outline the overall situation, kind of like I have here. So we outline the overall situation, differentiate it with respect to time. Once we have that derivative with respect to time, we'll go ahead and possibly get some information at that given moment and substitute into that equation where we're differentiating with respect to time so that we can solve it. So, Calc students, good luck to you. Please ask if you have any questions. Have a great day.